5.5. So this one is a bit complex, okay, very length in terms of the formula, but it's not that really hard basically, okay. It's the concept of pressure loss, whereby we have a pressure drop due to the viscous effects, okay, whereby you have data PL here, the pressure loss, okay, and the F is the Darcy friction factor. Normally F for circular tube is 64 over RE, over the Reynolds number, so it's rather easy. L over D, L is length, D is diameter, rho V average, okay, velocity over 2, okay, and valid for laminar, turbulent flow, circular, and pipes with smooth or rough surface. So it's quite versatile equation, okay. And this one is pipe head loss, okay. If you ever want to know the height that the fluid needs to be raised by a pump, okay, in order to overcome the frictional losses in the pipe, okay. So based on PL, you will know the HL because you have to divide this value with rho G here, okay. And of course lah, you can express in terms of PL. Then the utmost important is this one, okay. I would rather suggest you to take particular attention to this one because it is much more important, since they are the power needed for to pump that liquid, okay. So it is in unit of watt, okay. So this one is the volumetric flow rate, okay, and then you have to determine the value of HL first, okay, and then only then you can know the value of W dot, okay. So well, basically it is originated from delta PL, okay. So this one is basically just to ponder on how to determine the volumetric flow rate from the velocity average velocity and the cross-sectional area, okay. So you have to be very careful because there are so many terms in terms of area, right? So you have frontal area, which correspond to the drag coefficient, right? CF just now. So please look back at the theory of CF or CD, right? Okay. You also have surface area, which is AS. Okay. Normally this one is pi LD, and you also have AC. Okay. Pi d square over 4. Okay. AC is pi d square over 4. Kalau tengok before this punya ni, you have to remind me back lah. Okay. I think AC ni is pi d square over 4. Okay. Atau 2 pi r square. Okay. 2 pi r square. Kat sini dah betul lah. Okay. So please be very careful lah. Okay. So this is the power needed for pumping power. Okay. Alright, for laminar flow in tubes, we have here, okay, for constant QS, you have a constant value of Nusselt number, so you can always know what is the value of H from this value, okay. And then the friction factor is 64 over RE, just like the previous slide just now, this one, okay, here. And then you also have the same setup or the same trend with other geometry tube, okay. For constant TS is 3.66, okay. I think this one is not as much important as to compare with this one, okay. I think the one that you need to take particular attention is this one, okay. We will use this one in the example, okay. This one for circular tube, okay. This one by Edward and this one by Cedar, okay, which involve bulk, viscosity, and this one the viscosity at the surface. Okay, so this one is hydraulic diameter and so on and so forth. But for parallel plate, right? Parallel plate, right? So it's nearly the same with this constant TS, right? Okay, 3.66. But you have this term plus this one. Okay, that is entrance region, ya. Kalau ingat balik, if you look at this, yang this one, okay. So at this one, at this region, okay. Beyond that is fully developed, fully developed. So we are talking about entrance region. So this is the how you do you want to know the entrance region? So you have to determine the value of L, H or LT. Okay, LT or LH. Okay, I will show you after this via example. Okay, this one is very long example. Okay, no problem. Let's go one by one, yeah. Okay, all right. Let's go with this example 5.5. You have um, to consider the flow of the oil at 20 degrees C. Okay, and okay, the flow of oil. This one is 20 degrees C, Ti. Okay, and you know that the Ts is always so-called um, constant. So you know what is the formula that related to the constant Ts. Okay, and then you also will basically um, look at the Ts, which is 0, okay, constant. And measurement indicate that the surface temperature is nearly 0, disregarding the resistance of the pipe, and determine the temperature of the oil when the pipe leaves the lake. So you can use, you know the Ti, you know the Ts, so you can use this equation. Okay. But unfortunately, you don't even know the value of H. Okay. So how do you want to determine the value of H? Is via Nusselt number. When you know this, you will know what is the equation that related. So the first thing to do is to determine the RE dulu. Okay, RE dulu. Okay, so the Renault number is berapa? Okay, and if it happen to be in what region? Okay, so you better watch out the region we are talking about. Okay, it's either turbulent or laminar. Okay, turbulent or laminar, LT or LH. Okay, if turbulent, no problem. Okay, and uh, you will get the entry length. Okay, and then you have to compare. Okay, just now you are looking at the RE, right? RE is VD over nu, right? Nu is being given to you. Okay, V, is it being given to you? V, yes. 2 ms being given to you. And D is also being given, of course. It's 0.3. Okay. So you will get Renault number. Okay. And then it is either laminar or turbulent. Okay. And then you have to determine the LT or LH. Okay. And what might be the value. Okay. And then you start comparing with the length of the pipe. So it happened to be like, let's say the L is 20, so your length is 200. So of course, it is in the maybe more than that lah. Okay, it is in the region of the you call develop. Okay, developing region, entrance region. Okay, so bila the entrance region, so you can use this formula lah. Okay. China entrance region, you will look at, let's just go to this wait I'll try to show you in the PowerPoint solution in the PowerPoint. Okay. We go to this question. Okay, 200-meter long. So that's why the Renault number is 600. The entrance length is basically, if you calculate the length, because it is laminar, okay, and it will become 100,000. So of course it will become a developing region, okay, developing region. And then that is why you can employ, because the length is 200 meter, right? So in order for you to have fully developed, you need to go beyond this length. Okay, so it is impossible to do that. So of course you will have um, so-called thermal developed, okay, ataupun developing region, entrance region. Okay, so you can use this formula, okay, and to determine the Nusselt number, okay, and then this formula, this Nusselt number, so then you can get the Nusselt number, and you can always get H here. Okay, once you get H here, a S is also being provided to you, okay, pi LD, okay, L is 200, D is 30 cm, 0.3, M is being given to you, M, this is quite tricky, because M you have to determine from this value V, okay. Okay, M dot, okay, it's basically V dot, okay, you M over rho, so V dot is M V dot times rho, okay, M. So you know that V dot is basically V average times AC, right? So V average times AC times rho, you will get M, okay. So this is the value to be included in the equation. Cp is already there, yeah, right? Okay, and then you will get Prandtl number, of course, in here, and you will get H. So by using this equation, you can get the value of temperature TE. Okay, once you know the TE, so you can determine basically the value of Q. Okay, just sum up the value of Q as mCp delta T, okay, which is delta T is TE minus TI lah. Okay, from the TE yang you dapat tadi, this one. Okay, so you get X, you get this value, and for W dot just now in here, okay, W dot this one, okay, so you have to determine this value first. Okay, once you determine this value, you times with V, volumetric flow rate. Okay, F is RE over 64 over RE. Okay, LD you know, V average you also know, and then rho you also know. So you will get, just to plug in the value saja. Okay, no problem. So the answer is being shown to you here. So TE is 19 degrees Celsius. You have Q of negative 67.5. You know that the negative, because of the T surrounding, is lower compared to the T surface. Okay, I mean T fluid. Okay, sorry, T surrounding is lower than T fluid, or T surface is lower than T fluid, and then you have W of 16.8 kilowatt. Okay, or you can always instead of mCpDT, you can also compute M HAS delta T log mean. Can also, because you already know TI, TS, and TE, so you can determine the T log mean. So the value will be the same, this one or this one, sama. Okay, right? Okay.